Yep. Okay. So there is nothing new today at all.
Please excuse the interruption.
To move it. Yeah, exactly. Okay. So like I said, we're not learning anything new today. You're just going to learn how to use the second derivative test as another way to find max and mins. Okay? So thinking about this, if you find at f prime of c, if it equals 0, obviously that's a critical value. Well, c would be the critical value, right? Now, if you put that critical value into the second derivative, and that was greater than 0, aka a positive, okay, that means it's concave up at that point. Now, if it's concave up at that point, what does it have to be? This would have to be a local min, right? Because it's obviously at the bottom there, right? At x equals c. So it's important to know that when you find that critical value, you can put it into your second derivative. You can do your interval test like we've always been doing, but that would be your other way to do it. Now, if this is the critical value again, and you put it in and it becomes a negative at that point, so negative, right? Concave down. So therefore, it must be a local max at that point. Okay, so just note that critical values for the second derivative, if they equal 0 or undefined, it's difficult to interpret. So you're going to have to go back to the first derivative test. And we'll talk about that in an example that I kind of have for you. So we're just going to practice, or I'm going to show you how you can use the first derivative to find max and mins, or the second derivative to find max or mins. Okay, second derivative, we've always thought, oh, that's just for inflection points and concave up, concave down. It's good for that too, but it'll also help you find your max mins. Now it said find the local max mins. Now whenever you hear max mins now, you should be thinking first derivative, right? So f prime of x equals, what's the derivative of this? 6x minus 6x squared. Okay, let's factor it. We'll make it equal 0, and we can take out a 6x, leaving you with 1 minus x. So your critical values are 0, 1. Okay, so let's do it like we've always known how to do it, f prime x. Just this once, I want you to see how they'll give you the same answer. So we have 0 here, we have 1. Let's test some values. Let's test negative 1. If we put negative 1 in there, we'll get a negative times a positive. So that's a negative. If we put in, I don't know, 0.5, that would be a positive times a positive, which is a positive. And if we put in, say, 2, that would be a positive, and that would be a negative, so that's a negative. So we would have decreasing, increasing, decreasing. So we would have a local min at 0, comma. Now if you put it in to your initial equation, you get 0, comma 1. And you'd have a local max at 1, comma, put that into the original, you get 1, comma 2. Okay? So that's how you can find max mins. Now, or you can use second derivative. And first of all, you have to find second derivative. So second derivative would be 6 minus 12x. So now all you have to do is you sub in CVs from first derivative. Okay, in our case they were 0 and 1. So f double prime of 0 equals 6 minus 12. Well, actually, you don't even have to, I guess, you can just plug it in. F of 0 would give you a positive or negative? Positive. So that's concave up. Okay, therefore, it would have to be a min or max? Min at 0, comma, okay, put that in the original, you'll get 1. Okay, if you do f double prime, you put in 1. Okay, that'll give me a negative, which is concave down. So it'd be a max at 1, comma 2. Okay. So sub in your CVs from your first derivative. If they give you a positive value, it must be concave up, so it's a min. If it gives you a negative value, it must be concave down, so it's a max at that point. Make sense? So that's the only new thing today. You take the CVs from the first derivative and put it into the second derivative. Well, if you just had these CVs and plugged into here, this is quite fast. This is actually a pretty slow process. Draw the line, put your things down, find test values, right? So you wouldn't have to do any of this. But personally, I do like this way better because it gives me my up, down, and when I'm drawing my graph, that comes in handy. Because intervals of increase and decrease are needed to do this. So this, I don't see this being something that you're going to use. It might be just a question or information given to you that is a max at this point. Like that second question did on the quiz today, they just gave you information. So I may not give you intervals of increase, decrease. I'll just say at this CV, the second derivative gives you a positive. Okay, so it's just more of understanding the concept more than using it for graphing. Let's do, do we need to do both of these? Okay, let's try. Okay, let's do these. Okay, this is just good fun for remembering how to do our derivatives. Okay, so we want to use the second derivative to find the maximum. So we're not even going to do intervals of increase or decrease. So again, unless you like the quotient rule, let's change this to x squared plus 16x to the negative 1. Okay, derivative g prime of x would equal 2x minus 16x to the negative 2. Okay, we want to factor this. What can we factor out? 2x to the negative 2. No, we got to get first derivative first to get the CVs. Then we'll take the CVs and put them into the second. So that is, that'd be x cubed minus 8. Okay, so this would be just 2 times x cubed minus 8 over x squared. Okay, what would the CVs be? Yeah, 2 and 0. Okay, so then second derivative, g double prime. Okay, and I would go, to make our lives easier, I would go off this one. That'd be 2 minus, no, plus, right? 32x to the negative 3. Or 2 plus 32 over x cubed. Okay, now you want to plug 2 in there. So we'll do g of 2 would be a positive. So that would be concave up, therefore a min. Okay, so you'd want to try, now then you'd, so f of 2 gives you 12. Okay, now g of 0 would give you a does not exist because it's an asymptote. Okay, so just to give you kind of a heads up of what this would look like. So this would be 12, this would be 2. We've got a minimum at this point, and we've got an asymptote at 0, right? Okay, so that's got to be something that's like this. Okay. No, it might have a slant. Just let me see. Would it? Yeah, this one might have a slant asymptote, but we're actually gonna work on that. I'm not worried about that right now. Okay. This one here. So first derivative y prime equals. This is an easy one. Okay. Take out a 6, so 0, take out a 6, so I can be x squared minus x minus 2, 0 equals 6, x minus 2, x plus 1. CVs are 2 and negative 1. So y double prime equals 12x minus 6. Okay, so let's do when x equals 2, y double prime would equal a positive, so it's concave up, so it would be a min. X equals negative 1, y prime would be a negative, so it's concave down, so it would be a max at that point. Okay, and you have to obviously plug those into the original, and what did I get? 2 comma negative 2 was the local min, and local max was negative 125, I think. Okay, there's just kind of a note I want to add. Like, what if you have if f prime at c equals 0? Okay, so c would be a critical value, right? Now, if you put that critical value into f double prime c and you get the answer 0, Now, when you get the answer 0 of a second derivative, what does that mean? This is an inflection point. So it's saying that in the first derivative it gave a slope of 0. In the second derivative it gave the inflection point. Okay, so what kind of scenario would have that? Something that's like this. So right there would satisfy that. That would be a slope of 0 and an inflection point. So you're going from concave up to concave down, but you're staying from decrease to decrease if you did your interval test. Okay, so we're just going to do one question together of all the stuff that we need to know to be able to graph this. Okay? So, anyone have any idea what this would sort of look like before we get going? It would be a W, right? Okay. So we should be getting something that goes like this. Okay, what's the first things we should be finding? Think pre-calc before you, yeah, our y-ints. That's when x equals 0. So the y-int would be 0, 0. The x-int, that's when y equals 0. So 0 equals, I'm going to take out a factor of x cubed, which is x minus 8. So that's at x equals 0 and 8. I want to plug that into the equation. Okay, so that's 0, 0 and 0, 8. So I'm going to just, sorry, yes, 8, 0. I'm just going to put boxes around these. Well, I'm just putting these in boxes because when I have to go and grab everything later, I want it in coordinates. No, I just, and you see I mixed up my 0, 8, right? So even that stuff I'll find later, but it's actually, when you do enough of these, I kind of find on the very right side I put all my information, the far right, and then I just go and try and put it on these get to be a little bit overwhelming, so you need kind of a, okay, so we got those decks. What should we look for next? We don't have to worry about asymptotes, right? Or we should be doing that. We don't have any values that aren't allowed, right? Because it's not a rational expression. So what's next? Yeah, so we'll do, and what are we looking for at first derivatives? So max and mins. That's first derivative. Okay, so y prime would equal 4x cubed minus 24x squared. So 0 happens. We take out a 4x squared, leaving me with x minus 6. Okay, so CV's at 0 and 6. Okay, now we could go right to the second derivative, but I do find it is just always good to find my intervals of increase and decrease. So 0, 6. Okay, so I'm going to put in -1 as my first test. That would give me a positive and a negative. So I got a negative there. At 0, 6, I'm going to go 1. Put in 1, I get a positive and a negative, so I'm at negative. And 7 would be a good test value for the next one. So I have 7 would give me a positive and a positive. So it's a positive. So I have decreasing, decreasing, increasing. Okay, so I would have a local min at 6 comma, remember put it into the original, and you get negative 432. That is very minimum. Okay, and then put a box around it. Maybe if you have a highlighter or something, highlight all the stuff you know you're going to be graphing later. This is something important too, because I know by now that that's an S, right? Because it's coming down and it's coming down again. So it is giving me a slope of 0, but it's not changing from down to up, so I know that it's going to be an S there. And again, I could have found the max and mins by my second derivative, but second derivative doesn't give you all the increases and decrease. Okay, so let's do second derivative. So we're going to do, what am I looking for when I do second derivative? Concavity. Okay, so that's second derivative. So f double prime x should equal, where's my old derivative? Okay, so 12x squared minus 48x. So 0 would equal, I take out a 12x, leave me with x minus 4. So critical values for concavity would be at 0 and 4. Again, get my line going. Oops. This one, the one before it, I should have called f prime of x, and this f double prime of x. Critical values are 0 and 4. Put in negative 1, you'll get a negative times a negative. It's positive. Put in 1. 12 times 1 is positive. 1 minus 4 is negative. That's a negative. And put in a 5. 12 times 5 is positive. 5 minus 4 is positive. That's a positive. Okay, so I have happy there, sad there, happy there. So I got IPs at 0, comma 0, and 4, comma, if I plug it in, that's negative 256. And I want that for my graph. Okay, let's try and see what this thing's going to look like. Okay, so what do I got for, I'm going through here, this is my x int and my y int. And I'm going through 8, 0 as well. Okay. Now if I look at my first derivative from infinity all the way to 6. Okay, so I guess this was 8. I should start. This is 8. 6 is be about here. So all the way there, I am going down. Then after 6, it's increasing. Okay, my second derivative, I need to put a 4 on here because that was a critical value. From infinity to 0, I'm going concave up. From 0 to 4, I'm concave down. And from 4 to infinity, I am concave up. Okay. Inflection points. I have an inflection point here. I have an inflection point at 4, negative 256. So I don't know how big I want to make my scale, but maybe I'll put negative 256 here. So right here I have another inflection. I have an inflection point there. IP, and then those are my 2 inflection points. Okay, and I am missing a local min at 6, negative 432. So 6, negative 432. This is my min. Okay. So I know I'm going to start here, and I'm going to finish here. Okay, and you really want to do this drawing with a pencil on your test. You want to draw it and then double check, right? Because if you draw it wrong, you're going to notice it because something won't, and then you just erase it quick. But I'm going to be going in quadrant 2. I'm going to be going down and concave up. So to go down and concave, oops, I got to go kind of like this. Okay, and then I'm still going down, but concave down. So you want to kind of turn it a bit, so it goes like that. And now I'm still going down, but concave up. Okay, so I'm sort of exaggerating that it doesn't join perfectly there because I want you to see that I've actually done it in those sections, but of course it's continuous here. Okay, then I'm at my min. Okay, and then I've got to come up, concave up, and I've got to go through my and it would look something like that. And you can see from here, it says make sure you're going up all the way. So I am going up, and I'm concave up. Should look like that.
So was that at negative what it means in absolute?
Yep.
Maybe like if you asked us to label it on a graph, you calculate this.
You know what? If I would not give it to you wrong. If you put local min, so we're doing page 232, number 1, 2, 3. For all, just do the left column.